probable diagnosis for this patient is diabetic macular edema. You guessed it right. I am artificial intelligence. And I am working hand in hand with the ophthalmologist. AI is often perceived as a sci-fi dystopian future with man versus machine, when, in fact, it's quite the opposite. I'm here to show you what lies ahead.
Future Forward, Artificial Intelligence Assisted Eye Care. Artificial intelligence has already entered healthcare and is used for problems such as breast cancer screening, cardiovascular risk assessment, outcome prediction, planning of treatment, and managing records. AI has also made its foray into ophthalmology. It is indeed time we ask ourselves, are we, the ophthalmologists, ready for AI? Or do we want techies to define the way we practice in our future? We therefore decided to take matters in our own hands. We created 2 in-house models using AI, which were then used in our day-to-day clinics. Retinal OCT image classification using deep learning models. A retinal OCT classifier model was created using OCT images available from an open source. We trained the model with over 80,000 OCT images to identify 4 diseases: choroidal neovascularization, diabetic macular edema, drusen, and normal retinal configuration. Here, we use the ResNet-18 architecture. ResNet-18 is a convolutional neural network that is trained on more than 1 million images from the ImageNet database. A convolutional neural network is a deep learning algorithm that can take in an input image, assign importance to various aspects in the image, and be able to differentiate one from the other. The architecture of a CNN was, in fact, inspired by the organization of the visual cortex. The CNN reduces the image into a form that is easy to process without losing features that are critical for a good prediction. The model was given a set of 5,000 fresh images in order to test it. To make our model more relatable, we started with a user interface that looks like a web page. When presented with an OCT image, the model runs behind the scenes and gives us a predictive diagnosis. When the model was deployed, its accuracy in making the right diagnosis was close to 98%. However, in clinics, we would trust any model only if it is able to justify why the particular diagnosis was chosen over the others. And this is the explainability of the model. Whenever we look at the prediction from an AI model, a crucial aspect to consider is the confidence score of the diagnosis. Look at this example. Here, the model gives us a diagnosis of choroidal neovascular membrane. What's more important, the confidence score for CNVM is exceptionally high when compared to other diseases in the model. Let's look at another example. Here, the model picked up a drusen correctly, assigning it a very high confidence score. As a step further in the explainability, we use the class activation map to understand which were the exact areas and pixels of the OCT image that were chosen by the model to arrive at the diagnosis. We can clearly see what region of interest the model has selected to give the diagnosis. And it is very similar to what a clinician would choose. An explainable model instills confidence in the surgeon regarding its accuracy. More importantly, if an error is made by the model, it can be identified and the model retrained to improve its performance. This is why it's important that the ophthalmologist interacts with the model. An explainable, interactive AI model can be trained to get better and upgrade itself. Prediction of refractive error using ocular biometry with artificial intelligence. The most elementary in our practice is to determine the refractive error of the eye. We know that each biometric parameter influences the total refractive error. And yet, currently, the only way to determine the refractive error is by relying either on retinoscopy or autorefractors. So, we created a model that offers a completely new outlook to objectively determine the refractive error within an eye. Ocular biometric data was captured for over 5,000 normal eyes aged 18 to 45 years. This was input in regression models created using XGBoost and deep learning. Let's look at this case here. The model predicts a refractive error of -3 diopters based on biometry. When cross-checked by conventional methods, the refraction of the eye was found to be -3.5 diopters. Also, changing any biometric parameter automatically changes the refractive error. Understanding and exploring AI helped us get previously unknown insights into the contribution of different biometric parameters to the refractive error. If successful, this would be a completely novel way to assess refractive errors. There are several unexplored avenues where, if used correctly, AI will open new doors. The big fear that hounds us all is, will AI make the manpower redundant? The clear answer is no. In fact, incorporating explainable AI has the potential to take away the repetition in our lives, allowing us to focus more on problems that only humans can solve. Imagine how AI can be a boon in those regions and populations where access to basic healthcare is scarce and often challenging. But as with any new technology, amalgamating AI will also require us to make changes in our practices. The prerequisite to robust AI models is meaningful data. Therefore, we need to create a system that allows for accurate and easily accessible data. To sum up, explainable AI is the future. As clinicians, it is of paramount importance that we be equal and active partners with the industry in order to keep AI relevant, contextual, and ever evolving, so that it becomes a tool that helps us harness our potentials much better.